Okay, so thank you for a great presentation. We're joined now by Seung-seob to answer questions, and it looks like we're starting to get some questions. So we have a number of interesting questions coming in over Slack. So I'll ask some of those now. So one question, it looks like from Ji Huang at Max Planck Institute is if we ever want to address remote memory and GPU memory in a unified way, what kind of extension to mind could you introduce? And could we regard GPU memory as a special type of NUMA node in mind?
Great. Can you hear me? Can you hear?
Yes, we can hear you.
Cool, cool. So, yeah, first, thanks for the great question. I think there is the important next milestone or next research direction in resource distribution, especially if we want to support heterogeneous compute resources and also the other kind of resources. And one thing I can think of is the difference between memory consistency model between different kind of architecture. So CPU plays usually have its own memory consistency model, while GPU has another consistent model. And this is also not only between like CPU and GPU, but also even between CPU blades. One CPU blade having x86 architecture, while the other one has ARM and other architecture having different memory consistent model. So we need some extension that can translate or reconcile their disagreement in memory consistency model.
Makes sense. Sounds like an interesting challenge. So it looks like we have a live question from Marcos from VMware. So let's go ahead and ask that question.
Yeah, thank you. This is cool work. I was wondering, what is the memory model that you provide for the disaggregated memory in terms of the coherence? And that's one question. What's the memory model? The second one is, do you support atomic operations like compare and swap and so forth in your memory model?
Yeah, this is a great question. So currently you're considering the sequential consistency and TSO, the total store ordering model. And for the atomic operation, currently we are relying on the shared memory abstraction itself. So I do something, then the switch will block any other request or access to the same line, so that any other request will be rejected by the switch and they will need to wait until that request is actually committed and reflected inside the memory blade.
Thank you.
Thank you.
Great. So it looks like we also had a live question from Joel. Joel, are you able to, from UBC?
Hi, I really enjoyed this paper. First of all, I want to say that you actually used the word principles in SOSP, so that's great. Second, I'd like to ask a kind of an extension question. Obviously, your work is all about network and moving memory over the network switch. But what if we look forward to protocols like C6 or CXL, where we're basically scaling everything down to a network on chip kind of thing? Could you imagine building specialized hardware that would do the same kind of thing as your network switch? And what would you see that would need to change, if anything, if you were to scale it down to that size?
Thanks. This is a very interesting question. So I guess we already leave some minor comments in our paper, but we can think of two research direction or two direction of the industrial standard. One is, as you said, C6 and CXL that is focused on the network on chip and mostly focusing on the single machine. The other part is Gen Z, and who want to expand its memory space to multiple servers. So the major benefit in mind is as we place this memory management directly inside the network, so each module or node do not need to wait for the other node or the current. Usually we call it as a home node, which is responsible for such memory region. So we don't need to wait for the response from that node, but we can directly receive the response from the network itself. So that means we can reduce the round trip. And then I think this is the concept of putting something in network, especially for the memory management, can also help those industrial standard as a complement. Sorry, I think you're.
Oh, Joel, I think you're muted.
Oh, sorry. Posted writes. Like you write posted that you don't expect the response. You expect the response to come back asynchronously.
I think in current setup in mind, we make things asynchronous communication. So when I say in the previous response, in the previous Q&A, I said the switch will block the certain area when there's a request, which means that we need to maintain such synchronous currents between modules.
So Joel, thanks for an interesting question. Let's continue this on Slack. And in the interest of time, I just wanted to get to a couple more questions. So Shu Hao from UIUC had this really interesting question about what would happen if you scaled beyond a single rack? How could you extend Mind's design to work at a larger scale?
Yeah, there is another very interesting research direction, and I think this is one of the straightforward future research direction. And I think the core thought here is that should we still keep the centralized design over multiple racks? So in my personal thought, I think we can keep the centralized design only for the rack and tend those multiple racks as a NUMA node, so that each switch on the top of each rack is responsible for all the address translation and memory management for certain rack, while they can communicate with each other for further translation on the other rack.
Makes sense. So one more quick question with just a minute. So Marios Kogais from MSR had this question of whether you hit any programmable switch limitations. And I actually myself had the follow-up question. Is there anything you'd like to change about the programmable switch hardware?
So we are mostly, I think the constraint is from the line rate processing, because for the line rate processing, we need to limit the number of computing per stage, per path. So I hope if we can get more memory and also more longer or more powerful ASIC that can do more in a certain unit time, that will be really helpful. And also, yeah, I think the atomic stuff is handled by the locking mechanism in our switch.
Sounds good. Okay, so thank you for a great presentation, and thank you all for the wonderful questions. We're now going to move on to the next paper.
Hey, Samsung, thank you for the talk. I apologize, I forgot to introduce Samsung at the Seung-seob at the beginning of the session. He's a postdoctoral associate at Yale. He received his PhD from Yonsei University, Seoul, Korea in 2019. His research interests lie in the fields of edge computing, system design for disaggregated data centers, machine learning-based resource management, and system-level security. For the audience, please raise your hand if you have a question, and I'll promote you. Looks like we have a question from Enko here. Please introduce yourself and ask the question.
Hello, Seung-seob, can you hear me?
Yeah.
Yeah. Thanks for the nice work. I'm Ino from NUS. Yeah, so it's interesting that your work, Mind, used in-network aggregation using the programmable switch. So I'm curious if this Mind task for the programmable switch can be done by multiple programmable switches in parallel, or is there a requirement that we need to dedicate a single programmable switch for this job? And if that's the case, if we need to use the single switch, then what happens if the programmable switch crashes for some moment?
Yeah, thanks for the question. I think this is a great question.
Yeah.
So, can you hear me?
Yeah,
right.
I can hear you.
Cool. So, I think we can think of two different cases. So, we have one rack, but having multiple TORs, the top of racks routers or switches, so that they can communicate with each other. And in that case, we can have like two options, something like RAID series. So we can just duplicate all the data between those switches so that if one fails, the other can just continue. Or for the performance, or if we want to pack more data inside those switches, we can split the whole memory range into multiple switches so that they can serve the request in parallel, just as you said.
I see. So is the mind target the single rack environment, or it can be done through across the multiple racks?
Yeah, currently we are mostly focusing on only a single rack, and I think the multiple rack situation or more even scalable data center scale disaggregation is our obvious next research direction.
I see. So could you tell me the main challenge to extend your work to the multiple rack scale?
So one thing I could think of is when we have multiple switches, then they probably have another layer of hierarchy. So currently we just assume that every node is only located in a single hop from the switch, so that there is a new request they can just send out to the switch and directly receive the message. But if once we have multiple racks, then their request will be forwarded to another rack and then stored by the switch there. So so we need another layer of protocol, I guess.
I see. Thank you. Yeah.
Thank you. We have a question on Slack here. This is from Rito Ackerman from UBC. He says it's interesting work. How does Mind compare and contrast to Lego OS?
Yeah, so in our work, we categorize the previous work into two big categories. Some is in line of the DSM, and the other one including Lego OS, Fast Swap, Infinite Swap, all the other related works that leverage the page fault handling routine to grab the new data. So we share the same routine, so not actual swap system, but we still relying on the page fault handler to indicate whether the page is locally cached or not. But one big difference is that by putting the memory management inside in network, we don't need to worry about synchronize such metadata like who owns certain data. So for example, when I want to send new data from the compute plane, we don't need to worry about who actually owns the data. We can just send out the request with just virtual address, and switch will automatically translate the request and send it to the memory. But all the other related works relies on the cached metadata inside the CPU side blade.
Okay, thanks. I have one more question from Slack. This is Choi Ron from USTC. He's an MS student there. He says it's great work. His question is, what is the biggest challenge when integrating programmable switches in the disaggregated system?
Yeah, this interesting
question. I have a related question as you're answering. What would you like to have in future switches so that it can converse of that question to make it easier for you to program any MMU on it?
Right. So currently our biggest overhead was the computation of the switch. So basically to support line rate processing, the switching ASIC itself need to require to limit the number of computation per one pass. So once they put too many things, then they will not be able to serve packet in line rate. So I hope the future switch will have more computation capability, like more computation per cycle or per computation per unit time, and also having more capacity to store more entries, because that's the reason why I need to work really hard to come up with the dynamically splitting those entries in a dynamic granularities. I think you're muted.
Oh, sorry about that. Let's thank the speaker here, Seung-seob Lee, for that nice talk. Thank you. We'll go to the next paper. This paper is from Facebook. It's the RAS paper.